Hello, colleagues. I'm glad to say hi from St. Pete and Leningrad region. I am with the Supercomputer School of Polytechnical University of St. Pete, and Polytechnical University of St. Pete is huge educational and research cluster, works with many projects that have to do with AI, and I've highlighted one of the projects that we were talking about on the conference by our colleagues from Agencies for Strategic Initiatives, and I wanted to talk more about our student works, student projects that happen in our university, and while training in our High School of Intellectual Systems and Computer Technologies, we work with school pupils and students and retraining programs. So we have both the crazy ideas by the guys from the school or the students, and or wanting to just improve something that they saw or heard about, and we also work with experts in some fields and train them to become specialists in computer science. We have biologists, musicians, and people from different areas looking to apply AI. As part of the educational process, we touch on the disciplines that have to do with AI directly or indirectly. Machine learning is being used with all the typical algorithms and in data analysis. People work with Weka, Orange, Python, and of course we work with R a lot and train on this language for data analysis. In terms of HPC, our students are taught parallel programming, multiprocessor processing, distributed systems. They learn the standards like OpenMP and MPI for parallel processing, and they train to program graphic accelerators working with CUDA and OpenCL. So here are the topics for the diploma work or qualification works, dissertations by our students, and usually they are interested in the topic and would like to deeply to show deeply holistically, and like using deep learning to find bad photos, analyzing text or analyzing mobile subscribers, segmenting the users, working with data regarding expression. All the works are available on Polytechnical University's site and library. One of the topics in AI is analyzing the text and analyzing the tonality of the text. The task is to identify different aspects of the movie, for example, to explain whether or identify whether the users like or dislike the film, and to transform their words into numbers. One more task is to identify the aspects of the film that are liked the most or liked the least. So one of the dissertations was aimed at analyzing the reviews by people, actor work, the script, and other aspects. Of course, you need to take into account the variability of the language, the fact that people can use different words, synonyms, quasi-synonyms, and the fact that different aspects of the film can create different emotions. So, to solve for this, we use different tools, both the vocabularies, for example, and Yandex tools like Metaparser to find specific grammar structures, and with quasi-synonyms we used the word4vec model and libraries like Python and GraphViz for visualization. As a result, we were able to identify and quantify that attribution and tonality and to say which aspects of the film create positive and which create negative emotions. Besides just singular reviews, we had those graphs, those tonal graphs where we identify main aspects and areas and specific words that were used to discuss those aspects. Here's a slide showing two tonal graphs for different aspects of the same film, same movie. Something creates positive, some things create negative emotions, like the atmosphere. It can be used in a recommendation system to help the user understand, to provide the user with the recommendations based on his current mood and the thing that maybe right now the user doesn't want some negative, to watch a negative film and would like to watch a positive one. Also, besides using data analysis, we like algorithmical work where we try to improve the efficiency and effectiveness of the systems. So we have a supercomputer center that is used in the research, and I'd like to highlight the works that have to do with moving data analysis algorithms. The personal supercomputer allows you to run hundreds of threads and get a significant boost in performance. So this CPU to GPU transition is a complex task, because the GPU is organized very differently and the streams are turned into blocks. You need to use it wisely. You can create more threads, but then the thread creation is faster and the switching is faster, but we are not as free as with the CPU-based code. We need to remove merging, remove the branches and forking, and reduce the cycles. So we need to restructure the data and control structures. So here is an example with combination search in transactions, FPGA algorithm that builds a tree, but this is a non-balanced, non-binary structure. If we want to move it to GPU, we need to switch to flat structures, and we were able to get 7 to 8 times improvement in performance on an ordinary PC. This is not thousands, not hundreds, but it has to do with the convenience of the algorithm on GPU. And also, a more GPU-oriented task is matrix factorization, when you would like to build a forecast for, say, the scores that the user would give to a given film, a given movie. This matrix is very sparse. Users did not watch a million movies, didn't not read a million books, so we would like to predict those scores. And one of the approaches here can be to replace a very sparse matrix with their multiplication of U and V. They are more dense and they have concentrated information about the user's preferences and the objects. So using those two concentrated matrices, we can solve this task using stochastic gradient algorithm that SGD, that is a workhorse of ML, or ALS. So let's see what we can put here to optimize the calculation. So if we work with matrices, they can be symmetrical, and we can save up a lot of effort and resources working with such matrices. And if we take into account the sparsity of the matrices, then like with CSR formats, we will get only the scores that are present and only the formats that are optimal. We also need to use different approaches, like with NVIDIA we use scope-large, sparse, so specific to the hardware. And we need to think how we can parallelize that solution with thousands of threads merging into blocks. And also we need to understand how we work with memory. And shared memory is using faster memory can improve our calculation, but it has smaller size and you need some synchronization to work with it. And another growth driver can be tensor cores. With NVIDIA, you have tensor cores that allow you to run multiple operations of matrix multiplication within one tact, and they can be used for other tasks that have to do with matrix multiplication. So merging this all, we were able to gain a lot compared to the previous algorithm, growing 110 times, and be better than COMFALS. And our latest implementation is the second column from the right, and the competitor is the furthest to the right. So this is one iteration time. Finishing the presentation, I would like to thank you for your attention and say that AI did not pass us by, and we do our best to actually work on the best possible algorithms to analyze data and improve the algorithms. Thank you.